streaming. PC cam is working. Woohoo. Excellent connection. Share on Discord. Share, copy, Discord. Go to news and paste. Great. Can you check if the audio quality is okay in the stream? Okay. So today I would like to discuss with you the data which has been gathered on Monday for the photovoltaic modules, right? But I need your notebooks. But you haven't shared it yet, right? In exercises. Okay, cool. Exercises. Yay, cool. So I download it. Okay, where is it now? Can I open this? Okay, here. It's now here, and now I open my hub. I think I haven't opened it yet. So I use a new hub. Hub, Earth Observation Lab DE, Temp Lab, and so on. And with Control B, I can toggle the left pane. And it is part of electrical engineering here. And I would call this now, I need a new, add new folder. And this is in class, open. And I think drag and drop works. Let's see. Yeah, cool, it works. So then I open the notebook. And I move this to the first place, then it's easier for me to find. And I press F11 for full screen mode. Wow, of course, the images are missing. Ugh, of course. What can I do? Is it important? Maybe not. Because the folder, the images are in one of the folders, right? And we just copied the notebook, but there are these associated folders. Right?
Yeah, we should do as we done for the project. We have to zip the file and then get it from her and then unzip it in Jupyter. And this is a long process.
Oh yeah, you're right. The other thing is you can, the best would be to zip the whole folder, your whole folder, right? I can show you how to do that. Maybe I can show it on my laptop. Oh, sorry, I forgot that. But it's good, right? It's a learning process. So. No, it's good because you see these are things which happen, right? And that's real. And the same with, let's say, the problems in taking the data, right? You have some data glitches and so on. This is real. This is really how science works. It's never smooth. If you open the books, you usually see the very perfect curves and everything is smooth, everything is ideal. This is not the case. When you do your own experiments, you have a lot of errors, a lot of variations, and so on. So I can give you an example. Fatima, if you go to the folder, the root folder basically, where your no, go to the electrical energy lab course. What is it? Not the course preparation, the lab exercise 3, right? Okay, so we have to go to this folder, the lab WS 2022, right? Okay. So then open a new, where does that work? So does this work here? No, it doesn't. Open tabs, close tabs, kernel. I want to go back here. Open a new terminal. How can we manage that? Let's see if we can somehow edit, create a new, open New term. What is this here?
But you can just, I think you can just download it.
No, right click, I don't think so. Does it work? No, I don't think, but at least with the upload. We have a problem with the upload. No, okay, so new folder. Here, of course. You press this new launcher, right? Press new launcher, and then this comes up. If you scroll down, you can open a new terminal. Okay? Open a new terminal. I close this one. So, and if you chose here the right folder, it would then open the terminal exactly in this folder, right? Do you see this? Do you get that? Yeah?
Yeah.
Does it work? So when you press ls, it's for list directory, ls, it shows you all the folders, all the directories and files you have in that folder. Right? Okay, or you can say ls minus l, for example, is a long listing, and you see these are here preceded. So here are some indicators what kind of information that is, and D means it's a directory, and if you don't have a D, it's an ordinary file, right? So all the Ds are directories. So x3 is a directory, and we want to zip the directory x3. So the only thing you have to say is zip x3. Oh, sorry. Okay, zip x3. Oh no, really? Unzip? Gzip?
Maybe double P? Or?
No, I don't think so. Yes, it is a directory. How can I zip this? Okay. File. Decompress force. Isn't there a standard zip? Let me check. Because there is a way, of course, but it's a bit ugly. Okay, let me open a new browser window and search. So I could also ask ChatGPT, right? But I want to how to zip on Linux command line dash. Okay, how do I zip a file in bash? A folder. How to zip a folder? A folder. Zip minus R, but we don't have the zip. Hmm?
I think I have an idea. Maybe.
Yeah.
Like when we just need an data, right? If we can also upload that text file and we download to our PC and then call it, upload it simply. Will it not work? Because we have all the data.
Yeah, that's true. That's true. That's true.
But the data for Fatima has changed, so you have to download the data of exercises 3 on Fatima and then upload them in Jupyter. When you upload them,
But you are right.
you click on the terminal, unzip, and you get it. The point is now that we need to get exercise 3 of Fatima with the data and the images out of Jupyter as a normal file, and then send it on Discord to everyone, and everyone can unzip it in Jupyter.
Yeah.
The same as we done for the projects. But this took me in the project time.
No. It's okay. So there are several ways. Create set verbose file. I think x dot create set verbose file tgz x3. This would be a way, I think. Create verbose file. Why? tar minus set. Ah, okay, no, it's the other way around. It's tar, of course. Tar minus create set verbis file tgz. That would work. Okay, there is one way to do it, to zip the whole folder, right? You can use the good old tape archive, TAR, instead of zip, right? We forgot to install the zip function, but there is another one. Okay, Fatima, are you listening? Can you try to do this? tar, TAR for tape archive, and then a blank, dash, C for create, Z for compress, V for verbis, so that you see what's going on, and F for the file name. And you call this now x3.tgz. This is the file which will be created from the folder x3. That would work. But maybe it's too large, right? I don't know. What's the size? It's too big for Discord. It's 30 megabyte. I think we cannot share it on Discord, right? But your idea is good. So then let's do it for the data only. X3. We go to the data folder. X3 data folder. And then we can download them one by one. I think that is the right way, Fatima. Do you get it? So if you go to your browser, go to the file browser. Do you see this, Fatima? X3 data, and then right-click download, right? Individually, all the 4 files, or the 3 files, right? IV for modules shaded, IV for modules, and so on. Yeah? And then you would upload them one by one. That's the way. Great. Yeah. Sorry, the zip it's not there, but anyway, the zip file is too big for Discord. I think Discord accepts up to 8 megabytes or so. Or you have premium. I'm too poor. How to say I'm too greedy? I'm not. In German I would say too geizig. What is geizig in English? Great. So is it on Discord? Okay, we should have 3. Great. Great. Yeah, okay, so I can download them. 4 modules shaded. Then the next one. And the next one. It's this one, right? Download. So I go to the folder of the download. I thought I would. It doesn't change. Why? I hope it's in the open. No, I don't want to open it. I hope it's in the, no, that's wrong, in the download folder. Ah, yeah, it's in the download folder. Okay. But I just have 2. So modules shaded and modules shaded with diode. Name, IV, here they are. So now I do a drag and drop on my data. Good, which means I would rename the old ones. Maybe I need them later, I don't know. Backup, rename. Backup, modules, rename, backup. Okay, cool. So then 4 modules shaded, and 4 modules shaded with diode. So now the data should be there. And now I have to close all that stuff here. And start the notebook associated with this data folder, which is here, module exercises, Control B. So now let's see. Execute, execute. I press F11, okay. Or I can also run all the notebooks or run all cells. Let's see if that works. Okay, this is the first one. This is not too bad. This is also okay, believe it or not. But here is a mistake. We will see this later. And this one is also very good. Okay, so what's going on? So the first experiment which we did, so basically that was the second. We skipped the first one, right? The first one was just one PV module. To speed up, we said, okay, let's use 4 in series. So again, which voltage would you expect for one of these modules? Open circuit voltage. That is for a single cell. Very good. It's a single cell, but in this case it's a module. And we measured it yesterday or on Monday, and we found out it's 6 volts instead of 0.6 volts. What does it mean?
6 volts?
It's 6 volts instead of 0.6 volts. Fatima, say it again. N cells? Yeah, so we have 10 cells in series, right? So one cell is 0.6 volts, 10 in series is 6 volts, which means the plastic thing we see here in this photo, here, right? One of them is not just a cell; it is a small module consisting of 6 cells. Okay, so then we connected these 4 modules in series. So we didn't do the performance for one single module. So we have these 4 now in series, and the open circuit voltage. What would you expect then? Let's say there is nothing connected here, right? The load is not there. The resistance would be infinite. Which voltage would I expect here? Exactly, 4 times 6 volts, right? It's basically a review. It's a repetition of what we've already done, right? So, roughly. Okay. Then we basically set up the system. We fixed the system such that especially the irradiance, that we have a current. Do you remember the current we set? The short circuit current? 20 watt? Milliamps. 20, around 20 milliamps, right? So what does this mean? We have this case, right? Open. And we have 4 modules in series, which means, oh no, sorry, short here. We have, so this is open, right? Then we measure the open circuit voltage. And when we have a short here, the current which we are measuring, right, in series with this short, running through the short basically, is then the short circuit current. Okay. And which voltage would you expect if you have this short? Which voltage would you expect if you have this short here?
It will be the maximum, the 20.
So how can you have a voltage difference of 20 volts here if these 2 points are at the same potential? It's a short, right? This is one wire, this is one node, one potential. All of that here is one potential. So what's the potential difference? of course, 0, right? In fact, you would expect 0, but the wires are, so 0 volts, but the wires are not ideal, so there is some resistance here in the wires, right? That means there is a small voltage drop, but it's negligible. Okay, good. So this is a performance curve of 4 modules in series. So I think what Jihad basically forgot was to substitute here the open circuit voltage. This is the old, I think this is the old value which I initially added to the files, but you have to overwrite this, of course. So can you look up your notes? What was the open circuit voltage for this example? You shared them also on Discord with me.
For the first one?
4 in series without.
After the 15K.
So it was, I think you maybe you measured in the beginning, right? The open circuit voltage. These are your notes. They are awful, right? I saw you how you took the notes yesterday. I'm not willing to discuss with you what you have noted down. This is your personal mess. Find your way through your numbers. I'm asking you, what is the open circuit voltage you measured 2 days ago? Look at your notes. Yeah, you're laughing, right? Okay, give me your notes. I can show this to the students, right? This is so hard. Right, this is an excellent, this is an example for a very bad lab notes, right? Look at this. Or I have also here, right? I can put it down here. So you see, we have good reasons why we. Okay, I have to rotate it somehow. How can I turn the image anyway? So I can move it do it like this, right?
But here, for example, when it starts with almost 0 volt and the 20 milliamp.
That's 20 milliamps, yes, of course. Yeah. But so I'm asking you, what is this? Is this short circuit or is it open circuit?
When it's 0 volt, so it's the short circuit.
Exactly.
Yeah. So it's start with the short circuit, but the open circuit I haven't wrote it. But it's supposed to give the maximum voltage.
Yeah.
It's around. It was supposed to be 22.5 or 23.
Okay.
Yeah.
So you see, but that is not good science, right? And it's good that you are sharing this with me. That's what I said, right? This is about diligence in the lab. Yeah. It's okay, right, for now, yeah, because I did not formulate the requirements and we were in a rush. Yeah. But you see, the problem now is you try to discuss the problems you have here, and then the question is, where do they come from? And I'm pretty sure that this value here is because you forgot to note down the final here, right? The VOC, voltage open circuit, right? That is the value I added, and this is something you should have, of course, replaced with your own measurements. So that would improve the situation here,
so
right?
So the curve wasn't supposed to go back to 20?
Of course not.
Yeah. Thank you.
Of course not. So here is, of course, a big drop. Difficult to say where this really comes from. We had a lot of problems with the cables, as you said, right? But usually the idea, but we were in a rush, right? The idea of this experiment in the lab would have been add a point and reprint. Add a point, reprint, right? Plot. Add a point, plot. Add a point, plot. Add a point, plot. Also to assess the quality of your measurements. It's good that it's like this, right? Because this shows what could be improved, let's say, in a diligent lab exercise, right? Preparation. This here as well. So we had a lot of problems with the very thin cables for the panel. But in fact, what we would expect is a curve which looks like this. So it's pretty much showing the principle, right? And you see there is more or less a plateau here, and then we have a drop in the current when we are above a certain voltage here, and that is in fact a result of the diode, which is the simplest equivalent circuit model for a photovoltaic module, right? So how can I turn the camera around? I have a remote here, so how can I turn that? Front, back. I have EV. How? Maybe I have to do it here. Oh no, this is just... How can I turn the camera? Of course I can simply turn my smartphone, right? Okay, let me turn my smartphone. Cancel, okay. That works. So let's go here, desk. Good. So we discussed this in class already. I showed you these performance curves. And you can find, if you want to dive deeper into it and the deeper reason, you can find it in Volker Quaschning's book, right, on renewable energy systems. And I think that also Professor Buda in her class in energy technology will explain it again, probably with a different focus, right? So we have here the characteristic curve, let's say V and I. And for, let's say this is maybe 1, this is 2, 3, no, this is 2, 4, 6, 12. Oh, it's getting too long, I think. So 1, 2, 3, 4, 5, 6. No, it's okay. 14, 16, 18, 18, 20, 22, 24. 24 volts, right? This is the voltage in volt. And the current in amperes, let's say, or milliamps. Let's say this is 20 milliamps. So one of the cells would have looked like this. And not the cell, but the modules, right? So this would be this is one module with 10 cells. 10 cells times 0.6 volts per cell is 6 volts open circuit voltage, is this point here, right? And this here is the short circuit current. Okay, so then when you add another one, you simply add this curve to it, right? And then you have another one, you simply add this curve to it, right? And then you add another one, and you add it a fourth time, right? This is how the curve changes when you add more modules. Okay, so you see that the principle of this curve is still shown in the diagrams of Jihad. So this is really cool that we have this data to discuss, right? Thank you so much again. Okay. So what was my point? I hope you remember that we have here a current source. So this is now the equivalent circuit. Equivalent circuit of a PV module or so, right, or a cell. And the simplest one is this. It's just this diode which reflects the internal PN junction, right? So please look it up in the slides if you are not familiar with this anymore. And this is the photocurrent I phi phi for photon, right? And I phi is proportional to the irradiance times a constant, right? So this is just a constant. It's not the speed of light. This is not the electric field. This is irradiance in watt per square meter. And this is, let's say, a kind of photon efficiency or something. Photon efficiency. So that tells you of your irradiance, right? How much current is created from your irradiance. So it's this model, right? And I hope you remember from the experiments we did with LT spice that the current voltage characteristic, 20 milliamps or so, looks like this. This is from LT spice for this simple model, right? This is the performance. So we are here, we have a load, let's say a load or something, right? And then we measure the voltage across this load between the terminals of the cell, and we are measuring the current, let's say at this point here, for example, right? So we are measuring the current we are extracting, and we are measuring the voltage across this R. And then the performance looks like this, 0.6 for one single cell. This is one cell. Right? And then you are adding 10 cells. So one cell is like this, and 2, and so on, right? And then you have 10 of them, and then you are here. Then you have your module. And another 10, you are here. And another 10, and another 10. Okay? So, and now what is to be expected is when one of these, you have now 4 modules in series. And I have this in the notebook. So you have 4 modules in series, right? 4 modules in series, and one is shaded. What then happens is these are still generators, right? They are generating energy from irradiance, from your watt per square meter. There's amperes coming out of it, right? And voltage. And if one of them is shaded, this guy here, so this is a battery, this is a battery, and that is a battery, right? And what now happens is that this here becomes a consumer. It's like a device which consumes energy, which means it's dissipating the energy which is created. It's getting hot, and it can also be destroyed. This is a serious problem in all real photovoltaic installations. This is where you see the hot spots, for example, on photovoltaic modules. Some people are using thermal cameras, for example, to identify the hot spots and the damaged modules and so on. Okay. Yeah.
If one of these module got, like, something happens to one of these modules, so then there will be like no voltage anymore, because since they are in a series.
There will be no current. You will see the voltage is still there, but this is basically the experiment which was done here. So here Giat forgot to measure the short circuit voltage at this point. Yeah.
I have measured
current.
Yeah.
Yeah.
It was at 0 volt, it's 1.74.
Okay, great.
Yeah, but the one that it shows at 20, it wasn't believable.
Ah, it's this one. Ah, yeah, okay, okay. So we can simply remove it. Thank you. Cool. So this is now fixed. Right, right. Now it looks like this. But look at this. Look at the scale. Right. Let's rescale the axis. Let's say to 20. X1. Which one? Which one? X1. No, X0. So this is the first diagram. And I now fix the range of this diagram. Set y-lim from 0 to 20. Oh, type error. What's wrong? What? Oh. 0 to 20. Okay. You see? The same scale as we had before. And this is also advisable, right? When you compare values or experiments, right? And you expect, let's say, similar ranges, scale all of the diagrams to the same scale. Don't use auto-scaling if you really want to compare quantities in different diagrams, right? And now you see what's going on here, right? Do you remember what is the maximum power point here in this diagram? Right? What is the maximum power point? So we have these points, right? And each of these points has a voltage and it has a current. And the product of it is the power for this point, for that point, for that point. And at one of the points of your measurements, it's max, right? Here. It's this point. So this is the maximum power point. So in a real PV generator system, a large one, you would use so-called maximum power point tracker, where this load here is replaced with a special electronics which sets the environment here such that the maximum power is extracted from that system. So it adjusts basically your working point dynamically. For example, when you have a lower irradiance or you have a partial shading or whatever, right, then the maximum power point might change. And that is the reason why we use this maximum power point thingy. So, and our maximum power point tracker would probably use this point. We don't know exactly if this is really the maximum power point. Maybe there is another one here or here which we haven't measured, but it's somewhere here, right? It's always in the knee, somewhere in the knee. And you can see this here. This is the power curve where we simply multiplied V and I for all of the points. Okay, so now look at this. Where's the maximum power point? Look at the scale, right? And this is wrong. This is wrong data. As you can see, this does not fit this one because you can see, I think it does. It is wrong. Is it wrong?
It's just scaled differently.
No, it's not. I have to rescale it, right, to 350. Let's see if the data is... module shaded. No, it's okay. It's the same data. It's okay. It's okay. No, it's okay. Okay, then let's fix the Y limit. And this time it is for the power, and you see it was 350 milliwatts. So let's fix this one here to 350 again. Ta-da! So you see, in the unshaded case, you have 350 milliwatts, and now you shade just one of 4 modules, just one, and the power drops to 10%. And this is a big problem in reality. And what you then do is you are using bypass diodes. And this is the trick to overcome this problem. You are adding a diode across, let's say, a bunch of cells or modules, right? And basically this shortens, this bypasses this module. Instead of the current flowing through the module and consuming power here, it's simply bypassed and the current flows like this. This is very tricky also conceptually. So what happens here if this becomes a consumer, then the potential at this point gets higher than here, which means this diode here becomes conducting. In the case it's a generator, this potential here is higher than that one, and the diode is blocking. Right? So that basically is only active when the photovoltaic module becomes a consumer, or the cells which you have here. Yeah, exactly. Usually you would do that, and what you do in fact is that, because it's a bit, diodes are not that expensive, to be honest, right? But you have to somehow mount them in, and they are integrated in the modules, right? If you have a large let's see. Bypass diodes, so PV module. Bypass diodes. Do we have some images here? I don't know. Here, for example. So here you see you have three bypass diodes. So you are combining series of cells, right? And after let's say a certain number of cells, you use one bypass diode to just deactivate the problem you have here, right? So for example, this one, here's a shaded cell, which means this part here, that becomes a consumer, but it's very difficult technically to add for each individual cell a diode. Therefore, you are basically deactivating a whole block of cells, right? This is the idea. Is this clear? And that's basically the reason. Here, right, this is another diagram showing basically the principle, right? So you see you have here a series. So basically here's plus, right? Here's plus. Here the potential is the highest, right? And then you see here this diode would block because the potential here is higher than there, right? And then the current flows, what is it? These are basically the electron flow from negative. Oh no, let me think. No, it's the current flow, right? Because these are generators, so these cells are generating like a battery. So this is the plus terminal. And the other side is the negative terminal, right? So this is more positive than that, this is more positive than that, and so on. And it goes down like this, right? And here's the most negative. Let's say this is 0, plus 0.6, plus 0.6, plus 0.6, plus 0.6, and so on, right? And 0.6, and then you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this point would be 14 times 0.6 volts higher than that point. And this diode would block. But in case you have one module shaded, the potential here across this diode is reversed. And then this here is a lower potential than that one. And because basically here the current is kind of interrupted because of this consumer, then this diode becomes active and bypasses all of these cells. That is basically the reason and how it works, right? And technically you have maybe 2 or 3 of these diodes in a real module. And here, for example, you see here the bypass diodes, which are in a box below, in the connection box of the PV module. I don't have a good diagram, but here, for example, you can see where is it? Here. Right? What happens when a full segment here becomes a consumer instead of or here, right? You see here these hot spots, or here hot areas, here also, right? Hot spots in photovoltaic modules or photovoltaic installations. And these diagrams you already know, right? You see it's pretty common. Here are the bypass diodes, which are then connected to the cell internally. Okay, this is how it's done technically. Okay, so this is now, and what now happens is, this is also good data, right? That's what you would expect. So you have 1, 2, 3 modules. So let's say 1, 2, let's say 6 volts, right? 2, 3 modules still working, and 1 is bypassed. So this drops, let's say, to the energy you have here, right? To the current you have in the, so when you go for very high voltages here, the current drops to, let's say, less than 2 milliamps. That happens here in this case. But when you choose the external voltage to be less than that point, the system recovers, right? And now the maximum power point would be here. So it's much more than, and here's a problem. I think this is a mistake. DF4 shaded. This is diode. There is a typo, right? So you see here I'm calculating the power directly, where I say, okay, I have a data frame. It's like an Excel table. I use column milliamps and I use column voltage and I'm multiplying them. And here was a typo because the scale was not correct. Here, right? It looks like this. Here. So the point goes to 250 milliwatts. So ideally, you would have 350 milliwatts. When it's shaded, you have how much? What is it? Maybe 25 milliwatts or so, right? And if you have the bypass diode across the problem, it recovers at least to 250 milliwatts, right? So you don't get the 350, of course, because you have a problem, but this is feasible, right? And that's the reason why they use the modules. And you have a lot of problems with soiling of the photovoltaic cells, right? Dust, snow now, right? A tree, simply shading, bird poop, what have you.
I was thinking the connection is in series. Don't they think to attach them in a parallel way? Then we don't need a diode anymore.
Yeah, but you have to increase the voltage. That's the thing. Because later on, what you want is, I can show you. Oh, yeah. We haven't set this up. Ooga. This here so this is a real solar inverter. Let me change to OpSpot. So this is a solar inverter of the German company SMA. And because this is part of an experiment, but I didn't have time to set it up. So we have 20 modules in the Green Fab Lab, and we have 4 of these solar inverters. And how this works is, you can take it, have a look at it. You don't see much, right? Could you please take it? I should have opened it, right? But I didn't intend to show it, but anyway. So this is real hardware, right? So the idea of this is the following. You have, or let's say I do it the other way, like this, right? So we have 5 modules. 5 modules which are connected in series, right? So 5 modules connected in series. And each module is about 22 volts, right? So that means the total voltage. So and then, of course, that goes to this place here, right? And then you have here a, how do you call this? Module inverter, or let's say solar inverter. This is a so-called inverter. So this is direct current on this side, right? So there is no AC or something. And so what is the voltage difference here at the input of the solar inverter? So this is one PV module, right? It's a module, not a cell. PVM. Each module yields 22 volts or so. How much do we have in the end? 110 volts, right. Inverter input, 110 volts. But what you want to have in the output is 230 volts AC. And next week we will talk about what is AC, right? So you have a voltage which is modulated like this over time, right? This is the time, and this is the voltage, positive voltage, negative voltage, and we have an effective amplitude of 230 volts. So this is what you would like to have, because this can be then fed into the mains, and you can use it for your appliances, for example. But if this is, let's call this this is an island system, because this is really running on its own, right? Let's say which we call this, well, how do we call this? Maybe a PV generator, PVG, right? So this is a PV generator with this inverter, the module inverter included. And the idea is now that we have 4 of these PV generators. PV generator and another one. PV generator. And these generators are connected to a so-called battery inverter. Battery inverter. And this battery inverter has a 230 volt input. And here is your output. Because here is a storage battery. And this thing is really smart, because this is a kind of pacemaker. It generates, since this has a battery, it can generate its own 230 volts even on this input side with a certain phase, right? It's here, like this. And then these PV generators are smart. When you connect such a PV generator here, this side, right, to that side, what then happens is it detects the phase of this alternating voltage or alternating current, and it synchronizes to it. And then it listens, so this is from the battery, let's say from battery inverter, right? And then this is from generator, from PV generator. It synchronizes to it, and it's the same with the others. So all of them are then connected to this battery inverter. And this allows you to distribute these photovoltaic generators as island systems and combine them in one mains on your side, right? And then you have here the output, which is then fed by the battery or what is coming from here. But it's not so easy to really combine these power generators, because they have to feed in the power in phase, right? That means when this here is plus, this also has to be plus, right? And if this is minus, this also has to be minus, because otherwise you would counteract the power and you would dissipate the power basically in the system instead of being useful. So this is how it works, and therefore you need for these photovoltaic generators, you need high voltage. The higher the voltage in the input side, the better the efficiency of this solar inverter is. When you connect them in parallel, you are increasing the current, but you are not increasing the voltage. But you have to increase the voltage. That is the reason. That's a good question. Yeah, okay, I think that's it basically, right? That's what I wanted to discuss with you. And cool. Let me go back here. So you see, these curves are not ideal, but they show what is to be expected, right? So the ideal shape would be like this. And don't we have this book of questioning somewhere? Don't I have I don't know where this, I have the slides on my other laptop, right? I don't know if I shared it with you. Okay, so it's this will be the, I think this is clear, right? Let me go back here. It's this diagram. So let's say This is the ideal case, right, of 4 modules in series. It's like this. And then what happened is, I think I have blue. Don't I have blue or green? No. Okay, then I have black. So what happens now is that this is for the 4 modules ideally unshaded. So if one of the modules is shaded, it looks like this. Right? And if this module has a bypass diode, maybe I can use, what else? Blue, here. And if this module has a bypass diode, then it looks like this, right? It follows approximately. So 3 of the modules are still okay, and then basically it drops like that. And that's what you observe in the data, right? And this, I find this so cool. We designed this experiment last year. It was very hectic, but you see, this is the ideal 4 module curve. Here it drops to 10% or so, but the drop is really dependent also on the modules, right? But in this case, it's like that. And when we recover at least part of the problem, you see it looks like that. Thank you for listening. So how did you like that?
That's good.
Bit chaotic, right? Like always, but I think it makes sense, right? Because it's you see it's real stuff, real world. So, and I think I have an idea to improve my experiments so that it becomes easier. So, okay. So, so I